Hello and welcome to my video about the Doppler effect. So the Doppler effect describes a shift of apparent frequency in a wave. We call this the Doppler shift. And this happens with different types of waves. So the most useful version of this, honestly, is when we're looking at the stars and with light. So I'll mention it, but in Physics 20, which is what this video is for, light is not a requirement for the Alberta curriculum. So we'll talk about it, but we won't dive in too deep into the light aspect. More so, we'll look at sound. Okay, so we'll talk about both, but sound is more important. Okay, so when an object travels towards you, the frequency will increase, you have a higher pitch, or more blue. And when an object travels away from you, the pitch will decrease, i.e. lower pitch or more red. Okay, so towards you, higher pitch, away from you, lower pitch. So there's this formula that you have in your formula sheet, and then you should use the positive symbol with this plus or minus here. Okay, so you should use the positive symbol if it's moving away, and you should use the negative symbol if it's moving towards. Okay, so positive or negative depending on what's happening. So if the source is moving towards or away from the observer. Now this is relative, right? So it could be that the source is moving or the observer is moving. Either way, it works the same way, towards or away. So here's a funny just video to introduce the Doppler effect for you. And honestly, this is what I do. I literally use this to help me remember the Doppler effect.
Sean, there's something I want to talk to you about before we go to the park. I don't care if anybody gets it. I'm going as the Doppler effect. No, it's not. If I have to, I can demonstrate.
So honestly, I do that during tests, or at least in my head, I go meow, because that's the sound that a car makes or a fire truck makes or whatever as it flies past you. So as the car comes towards you, it's that first part, nyeh, it's a high pitch. And then when it goes away from you, it goes, meow, right? Nyeh, meow. So listen again.
Demonstrate.
Meow. That's the sound of a car driving past. That's what it is. That's all it is, right? That's the Doppler effect.
Terrific.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint.
A choo-choo train?
Close.
A brain damaged choo-choo train?
I still don't get it.
I'm the Doppler effect.
If that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra? Why don't you just tell people you're one of the 7 dwarves? Because I'm Frodo. Yes, well, I'm the Doppler effect.
All right, so yeah, this is that is just a funny video that helps me remember the direction of shift. But let's take a look at another video. Alt-Shift-X is the creator of this one. Let's take a look at this other video to understand really what the Doppler shift does. And I think I'm going to just make this bigger on this screen here.
So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in
So that's all I really wanted you guys to see there. That if we look back at this part here,
when the thing that is
emitting emitting waves, you can see that as it's moving here, I'll just go a little bit further. There you go. All of these waves are all close together because it moves towards the wave that it just created. And on this side, it moves away from the waves it just created. So those ones are more spread out on the white side and more closer together on the pink side. So while it's moving in one direction, it gets closer together. Okay? Now, on the other hand, we're going to flip it around here quickly. If you now look at it, it's moving towards the right and towards the eyeball. And when it's moving towards the eyeball, it is actually bunched up. And so it looks like it has a higher frequency when it's moving towards you. That's that higher pitch with the fire truck. And on the other hand, if it's moving away from you, it looks all spread out. So the frequency is actually lower in this case. And because it's lower, it has a lower pitch if it's sound. And that's basically it. So we're going to just take a look at a couple questions here. All right, so here's the question. I recommend pausing the video now and trying it out for yourself. Okay, so we've got large waves traveling quickly at 50 kilometers per hour, but infrequently, and only having one wave every 14 seconds if you're standing still. If you're piloting a boat on the ocean and traveling towards the source of some of these waves at a rate of 20 kilometers per hour, what is the frequency that you will experience these waves on the boat? Okay, so you keep in mind that you're traveling towards the source. If you're going towards the source, that's like the car traveling towards you. It's a higher pitch. So if it's a higher pitch, that basically means it's a higher frequency. So our final result should be a higher frequency result than the original. Okay? Now the original is 14 seconds. Well, that's one wave every 14 seconds. So 1 over 14 seconds. Okay, so we're going to plug all of this into our formula here. So we're going to have 1 over 14 seconds as our frequency for the source. And we're going to look at the wave speed. Now this is kilometers per hour. Kilometers per hour is not very helpful. So we have to switch it to meters per second. So at first we want to get rid of kilometers by getting meters instead. So 1,000 meters is 1 kilometer. So we're going to multiply by 1,000. Then we want to get rid of hours and get seconds. So hours and hours cancel. So 1 hour is 60 times 60, or 3,600 seconds. So it's basically like dividing by 3.6. Now I have it right here. So 50 times 1,000 divided by 3,600 is 13.8 repeating meters per second. So that is the speed that the wave is traveling. Okay, and we're going to take that value and we're going to either add or subtract by the value of our own speed going towards the wave. So now it's 20 kilometers per hour. And I mean, I can tell right away that I'm just going to do the same thing as last time, so 3.6, which is going to give us, so 20 divided by 3.6. Oh, whoops. Divided by 3.6. So that's going to give us 5.6. Well, 5.5 repeating. Let's keep that in there for now, so we don't round too early. Okay, so now we're just going to try it in our calculator and see which one gives us a higher frequency. So okay, hold on, use this. 1 divided by 14 times by 13.888888 divided by 13.88888. 8888888, and then I think it's minus off the top of my head 5.5, 5555555, bracket, enter, and we get the frequency of 0.119. Now, actually, that's kind of hard to tell if that is faster or not, but originally it was 1 every 14, which means that it is faster. It's a higher frequency. So subtracting was the right way to go. So I can get rid of that, plus or minus. Subtracting was the correct direction. Okay, and the way I know it is because of that stupid Big Bang Theory one, where it goes meow, right? So towards you, it's higher pitch. Away from you, it's a lower pitch. All right, so here's the next question. So I highly recommend pausing the video now and trying it for yourself. So a fire truck drives past you at a speed of 60 kilometers per hour, and the pitch of the horn is that. What is the change in pitch frequency that you hear? Now, keep in mind that we're just basically always going to use, the speed of sound in air as 343 meters per second. Okay, so use that value in order to solve this question. Okay, so now that we have that, we're going to go ahead and try to solve this. So the pitch of the source is 765 hertz. Oh, sorry, 56 hertz. Okay, and then we want to use the speed of sound, which is 343 meters per second. We're going to put that also on the bottom. And then we're going to subtract by the speed that the fire truck is actually moving. So keep in mind this is moving at 60 kilometers per hour. So just like the last question, we need to get it away from kilometers and hours and get it into meters and seconds. So just like the last question, you want kilometers to cancel, hours to cancel. Now I have meters per second. So we get 60 times by 1,000 divided by 3,600. And we get 16.6 repeating meters per second. Okay, so we can put that in here, 16.6 meters per second, and I'll leave it as repeating just so we can avoid having a sig-dig error. So we're going to have 756 times 343 over, and then we're going to have to put in brackets 343 minus 16.666666, bracket, enter. And so we get frequency as 700, it's moving past you. So here's the thing. It's past you. What is the change in pitch that you hear? So I just found the subtraction version, right? As, here, let's do it this way. So I found the subtraction version, which gave me 794.6 hertz. Okay, this is the higher pitch version, but now we can find the addition version of the exact same question. So everything else is going to be exactly the same. Except for, we're going to add the 16.666666, whatever, repeating. And so now we get 720.96. Hertz. And we can just subtract because we're looking for the change or the difference in pitch. Okay, so this means we're going to subtract here. Okay, so we're going to have 794.61 minus 720.967, and we're going to get 73.6 hertz. This is the change in pitch that we were able to observe. Okay, so here is the situation. We've got this formula given to us in this question. Now, this is beyond Physics 20, actually. This is an AP or an IB concept. It's one step above because light behaves very strangely, okay? But it's very interesting to look at, and so I'm going to show it to you anyway, but keep in mind this is above the regular Physics 20 curriculum. Now, in this question, when V is going to be positive when things are moving. Sorry, I'm going to use a different color. V is positive when things are moving away, okay, which means that we're red shifting. Okay, V is negative when things are moving towards an observer, which means that you're blue shifting. You're getting more blue. Okay, so red shifting means longer wavelength, which means also shorter or smaller frequency, and this means shorter wavelength, which means higher frequency, right? So that is the situation for blue and red. Now let's take a look at this example itself. So if the Doppler shift is going from that to that, it's hard to tell exactly, but basically this is the new value, okay, and it's more red, and this is the original value, which is more blue. So we need to change those, however, to be in wavelength. So wavelength is given by this formula here. So we have V equals F times the wavelength. But we know V is actually C because we're talking about the speed of light. So this would be correct. Now we're going to find the frequency, so we're going to divide by wavelength on both sides. So C over lambda is our frequency. Okay, now that we have that, we can figure out both answers. So we're going to figure out the red answer first. Okay, so we're going to plug in 3 times 10 to the 8 is, speed of light in a vacuum, divided by lambda, which is 2,000, and this is nanometers, which is times 10 to the exponent negative 9. This is something that you can find in your formula sheet, the times 10 to the negative 9 for nanos. So then we get the answer of 1.5 times 10 to the 14. This is hertz. Okay, now we're going to do this again, but we're going to just change it to, the different nanometer, different wavelength, which is 400 times 10 to the exponent negative 9. So we get 7.5 times 10 to the 14 hertz, and actually before it was times 10 to the 14, I just forgot the 1 part of the 14. Okay, so those are new frequencies there, and so we now have those. We can use those in our formula, but let's rearrange and see if we can solve for the speed of the star. Okay, this might be a little bit challenging, but hopefully we can get there. So F observed divided by F source equals the square root of this whole lovely, beautiful thing. Now, is it going to be, you know, the positive or the negative version? Well, maybe we can just leave it as it is, and we're going to find v, you know, if it's positive or negative v in a second, right? So this is what we get as our first step. Now we're going to square both sides. So v observed squared over vs squared, 1 minus v over c over 1 plus v over c. Okay, now we're going to move this over to the other side. This is going to take a little bit of algebra, but we'll get there. So f o squared fs squared times 1 plus v over c equals 1 minus v over c. Now we're going to multiply this into the bracket, so we get f o squared fs squared plus f o squared over fs squared v over c. Okay, now we can simply subtract by this first term here. We're going to subtract by that on both sides, so we're going to have v squared vs squared v over c equals, and then we're going to, like I said, subtract on both sides, so like this. Okay, now we're going to multiply both sides by c and by vs. I'm going to take this one step at a time. So c and then fs, squared minus, and then c is going to cancel, which is nice, v and then fs squared minus, and then the fs is going to cancel squared, but the c is going to stay, so it'll look like this. Now we're going to divide by the fo squared on both sides, so v, oh, we forgot to move this over. Nope, so we're going to move this guy back over this way now. So fo squared v plus fs squared v equals cfs squared minus cfo squared. Okay, now we're going to factor out the v's. We're getting there, guys, we're getting there. Plus this equals all of this. Okay, so now that we've factored out the c's, now we can divide, or the v's from both of those. Now we can divide by that on both sides. So we get c f. So we can also factor out the c's here, which will make it easier when we plug it into our calculator. All right, there it is. So that is a lot of rearranging to get there, but we were able to do it. So we got to this point. So we're looking for the velocity. Okay, so we're going to type all of this in. So 3 times 10 to the exponent 8 is the first c, times, and then the bracket, we're going to deal with the frequencies now. So of the source, okay, so let's be very clear about this. What is the actual source? This is going to be source here in blue, and the f observed is the red one. Okay, let's just make sure we're very clear on that. So the source is 7.5. Oh no, we're gonna have to put in brackets. 7.5 times 10 to the exponent 14 bracket, and then squared, minus 1.5 times 10 to the exponent 14 squared. That finishes off that bracket. We need to put one more bracket, and now divide by, and then the whole bottom, which is going to be, observe first, so 1.5 times 10 exponent 14 squared plus 7.5 times 10 to the 14 squared. And now we're going to, yeah, I believe that's everything. Okay, lots of brackets, but I think it's good now. So the velocity should be, and actually I'm concerned that we did it wrong because that looks like too big of a number. 1, 2, 3, 4, 5, 6, 7, 8. Hey! Okay, no, it does work. Okay, 2.76 times 10 to the 8. That is one heck of a speeding star. But it is possible because it is less than the speed of light. And oftentimes we'll actually, when it comes to numbers this big, we usually will actually take those numbers and have them as a fraction of the speed of light. So if we put in the speed of light down here divided by the speed of light, you can see that we'll get a fraction of the speed of light, which is 0.9. So V equals 0.923 C. So both of those answers would be fine and correct. But like I said, this is beyond the direct curriculum, but it is still Doppler shift, so it's a curriculum adjacent. So I wanted to show it for you guys, but don't worry about how difficult all that algebra was. It is still all doable algebra, but it is difficult algebra. So I hope this video helped you understand Doppler shift more than just the last question, but for all of these, the whole concept of, as Sheldon says.
Hey Sheldon, there's something I want to talk to you about before we go to the park.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow.
As he says, meow. Don't forget it. All right, I hope this video helped, and good luck.